Okay, everybody, so let's get going now, because today we are going to talk a lot more about clouds. So on Tuesday, we really started thinking about the processes behind condensation. How do we go about saturating air with moisture? And because remember, atmospheric moisture is so important. It's really what provides our fresh water here in Southern California and elsewhere on Earth, and we can't cope without pretty large amounts of it. So we want to understand a lot better how that moisture arrives in the atmosphere, how it's moved, and why we get rainfall. I mean, here in California, we're in a really very severe drought. And so it would be nice if we can understand what controls our rainfall, why we get rainfall. So that's going to be the focus of today. We're going to look much more about cloud development and different ways we can get air saturated. So a reminder, quiz 4 is available as usual, and it's going to be available from 4 p.m. today until 11 a.m. on Tuesday as normal. So don't forget to take a go at that. Midterm, a week today now, okay? And so it'll go from 2 to 3:20. I like long exams, so do make sure that you're on time, both so that you don't disturb people while finding your seat, but also so that you can really allow yourself a chance to think, because I don't like asking memorization questions. I really want you to be able to use the information I've given you. So really, when you're studying, focus on understanding, on concepts, draw things out for yourself, write logical sequences of information, make sure that you do understand. There is assigned seating, so a couple of left-handed people have emailed me already. Please do email me by Monday if you would like a left-handed seat, and that will prevent us having to put too many right-handed people in those seats. Things that you will need: pen and pencil, no calculators please. Any maths that I ask you to do, I can do in my head, so I'm sure that you can do it in your head. It won't be anything too complicated. The Scantron Form 288, it's the red one. Student photo ID, and then also optionally you are allowed to bring a sort of small note card, double-sided, with notes on, because I know that there are a lot of different words that we use in this class. I'm not interested if you can memorize those words. I want to know that you understand what they mean. I want to see that you can use them in a sentence, not just sort of throwing them in there randomly, hoping it's right, okay? So you're welcome to do that, but you will be handing those in with your exam, okay? Study guide is available on the website. I've also reopened a lot of the quizzes, so you can take them again as many times as you want now. Not quiz 4 this weekend, okay? But quiz 1 to 3 you can take again as many times as you want for practice. And also I'll be in my office from 10 to 12 on Thursday, the 1st of May, that morning, for any last-minute questions. And also we have a midterm review session, which is going to be on Wednesday, the 30th of April. I think I said the 31st of April on Tuesday, which doesn't exist. So the 30th of April, and it's going to be in PCB 1100, and the TAs will answer questions, okay? Does anyone have questions for me about the midterm? No? It's all clear? So, okay, great. Good luck studying this weekend. So, also midterm evaluations. I really want to know what you think. Okay? It's difficult for me in a class this big to really talk to that many individuals. So this is your chance to let me know how it's going. Are there certain things that I could do that would help you out, that would help you learn? Specifically things like the discussion activities. Is it giving you a chance to work through some of the trickier things to use, because we are a quantitative literacy class, is it giving you a chance to do that math in a helpful way? Do the quizzes help you understand topics? Anything like that. So I do value your feedback, and I will make changes if I can to accommodate that. So if you have a chance, fill that out for me. So first, iClicker question of the day. We're launching in early today because it's a bit of a review from last Tuesday. So which of the below could cause air to become saturated? If I decrease the vapor pressure, if I decrease the temperature, or increase the air pressure by compressing it? Which of those would cause air to become saturated? Right, so let's take a look and see if we remember all the way back to Tuesday. Why don't you have another think about that? Why don't you talk to your neighbor? Wave at me, TAs. One there, one there, one over there, one over there. Consult your TAs. Okay? So let's take a look and see if we get a better split this time. So I think people are getting confused because of the bottle. What happened to, well, when did I see saturation? At what point did I see saturation with my bottle experiment? Was it as I was pumping air into the bottle? No, when was it? When I released that pressure. And so that air, was it compressing or expanding? Expanding. So was it warming up or cooling down? Cooling down. Does anyone want to change their answer? Hopefully you do, because really the correct answer is B. Okay? So remember what we did when we compressed that air. When we compressed that air, we warmed it up. So we increased the saturation vapor pressure, we increased the amount of evaporation going on, but that wasn't the thing that made it saturated. The point where it became saturated was when we uncorked the bottle, and all of a sudden the air could expand very rapidly, it cooled down very rapidly, and so we moved from sort of a position maybe over on this side of my graph, we had sort of a high saturation vapor pressure, high amounts of the actual water vapor, and then by expanding it, I cooled it down rapidly and I hit that red line. So I decreased the temperature, I hit that red line, and I became saturated. And at that point, we got condensation. Does that make more sense now? Is it starting to ring a bell? No, it doesn't make any sense. So imagine that I started with, I don't know, my air temperature at 20 degrees Celsius, and I had 10 millibars of vapor pressure. As I pumped air into that bottle, I increased the temperature. Okay, so I increased the temperature, but I also increased the temperature of the liquid. We had more evaporation going on, so I also would probably increase a certain amount of the vapor pressure. So maybe we ended up here. We had warmer temperature and more vapor pressure actually in that air. And then all of a sudden, when I let that pressure go really, really quickly, it expanded really fast, and its temperature therefore decreased. And so I decreased my temperature without losing any vapor pressure. Okay? And so what happened was that as that temperature decreased, I crossed that red line, and so we started seeing condensation. That decrease in temperature as the pressure let go caused us to move towards saturation, to hit that red line, and that's when we saw droplets. Does that make a little bit more sense? Maybe? Good. Okay. So this is because we have these two different types of processes going on that can change our air temperature. And really that change in air temperature is what we see most often in our atmosphere, which results in us becoming saturated. It's really important in our clouds. So 1 to 3 there. So either by adding energy or losing energy by conduction or radiation, or by mixing air, different temperatures together by convection, or by changing the phase of water. Remember that sort of things like condensation from gas to liquid releases lots of energy, okay, which would warm the surrounding air. All of those things are adding or losing energy, okay? And so we call those diabatic processes. Energy is being added or removed. What we were doing with the bottle is looking at adiabatic processes. And this is where the total energy is, I wasn't like turning a hairdryer on and holding it over the bottle to warm it up. All I was doing was I was increasing the pressure. So if we compress air, it heats up. And if we expand it, it cools down. And this is especially important when we want to form clouds, because we have this amazing pressure gradient. We have really high pressure down here at the surface. But as we go up in the atmosphere, then we lose that pressure. And so if you imagine a balloon here at the surface, it might be this big. As it goes up in the atmosphere, as the pressure outside it is less, it's able to expand. And that's what happens to just sort of a parcel of air. As it moves up in the atmosphere, because the surrounding air pressure is less, it expands. And so as that air moves upwards, it expands and it cools down. And that cooling causes us to move towards that red line on my graph, causes air to become saturated. So let's look at this process. This is the last thing we did on Tuesday. We sort of tried to put these sentences into order to explain what's happening. So let's start at the base, at sea level, down here at the surface, and let's say that our air is 30 degrees Celsius. So really nice and hot, okay, for those of you that don't know Celsius. So let's take that parcel of air, and we're going to force it to rise. Okay, so we're going to take that air that's 30 degrees at the surface, and we're going to force it up to 1 kilometer high in the atmosphere. And as it does that, it cools down at a very set rate. The physics controlling that expansion and cooling is very set. And so we call this the dry adiabatic lapse rate. It's how much colder air gets as it moves up in the atmosphere. And it's a nice round number. It's about 10 degrees Celsius per kilometer. So by the time I get my parcel of air from the surface up to 1 kilometer in the atmosphere, then it's cooled down by 10 degrees. It's now 20. If I lifted that another kilometer up in my atmosphere, I would get to 10 degrees. If I added it another kilometer, I'd get to 0 degrees Celsius. And if my air was completely dry, if it had no water vapor in it, then that's just how it would keep going. It would just keep cooling down at 10 degrees Celsius per kilometer. But it's pretty rare for air to have no water vapor in it at all. And so at a certain point, we cool down that air enough that it hits my nice red line on my vapor pressure diagram. Okay? At a certain point, we cool it down so much that it becomes saturated. And at that point, we have something different going on. We have condensation. And remember, condensation releases energy. That process of water molecules going from being free-moving molecules in that air into a contained liquid form means that we release energy. And that energy just doesn't disappear. It goes into warming up the surrounding air molecules. So now we have two different effects going on. We still have this cooling of that air by 10 degrees every kilometer, but now we have condensation happening, and that adds back in 5 degrees Celsius for every kilometer. So we have a decrease of 10 degrees going in one direction, and an increase of 5 degrees going in the other direction. And so if we look at the net change, then we see that now we don't cool down at 10 degrees anymore, we only cool down at 5 degrees Celsius per kilometer. And there's one confusing thing about my diagram on here, and that is that they set their lapse rate, their moist adiabatic lapse rate, we're going to call that the saturated adiabatic lapse rate. They set theirs to 6. It's too complicated, I like rounding down. We're going to make ours 5. It's easier to deal with, okay? So our dry adiabatic lapse rate is 10 degrees Celsius per kilometer, and our saturated lapse rate, what happens when that air is actively condensing, is going to be 5 degrees Celsius per kilometer, okay? Does that make sense? Hopefully everyone's had a chance to think about that in the last 2 days. So, that's all very well, but let's look at some real cloud, and we don't have a good example today, unfortunately. So, let's have a look at some clouds from, how do you say that? Tucson, that place. So, this is a time-lapse of a cloud forming. I love time-lapse because they really show you bits of the world that you would never ever see otherwise. And you can see that really what's happening as those clouds form is that we have this explosive energy of air moving upwards, and you can see that, and you can see that air moving and condensing as it moves upwards and builds these beautiful clouds. So I think this is really cool. So next time you find yourself with lots and lots of time on your hands, sit out and actually watch a cloud and see if you can see it doing some of this, okay? So, fun stuff. So, second iClicker question of the day. Let's see if we can get a better spread this time. Where does the air in my picture here reach its dew point temperature? Does it reach it at A, B, or C? So remember back to what dew point temperature is. Okay, consult your neighbor if you can't remember. Okay, let's see if we get a better split this time. We do. That's much better. Good. Good. So we're remembering that the dew point temperature is the temperature at which air becomes saturated, the point at which we finally cool down that air enough that we reach saturation. And so where is that happening on my diagram? Well, if you imagine that we're lifting that air, it's cooling and cooling and cooling as it goes up until we hit this amazing sort of surface almost at the base of that cloud. And at that point, the air is cooled enough that it's become saturated, and from that point onwards, we're getting condensation happening, and it's forming our visible cloud that we can see in the atmosphere. So, given that you did that, this will be no problem at all. Which of those points, A, B, or C, which of those is air cooling at the dry adiabatic lapse rate? Almost embarrassed to ask, because I think this is a very obvious question. So let's take a look. Somewhat obvious, it seems. So, at what point on there do we have unsaturated air? C. Because at A, air is saturated, we can see condensation going on, and so air at that point would be cooling at the saturated lapse rate, because we both have that air expanding, but we also have condensation adding energy back in. So at A, we would have the air would be cooling at the saturated lapse rate. You know that because you can see water, okay? But at C, where we don't see cloud, we don't see condensation going on, that's where air will be cooling at the dry adiabatic lapse rate, okay? So hopefully that makes sense for those of you. So let's think about it. We say that clouds are formed by lifting air, but air that's sort of sitting at the ground doesn't magically just decide that it wants to go up in the atmosphere. We have to somehow force it to do that. So we're going to look at 4 different lifting mechanisms. So basically, how do we get air that's here at the surface to go up? And so the first and most obvious one is called orographic lifting. And it's basically just if you have a mountain in the way, that air doesn't move along. It doesn't just sort of reach the mountain and go, oh, well, it's too hard to go anymore. It's going to go up. It's going to go up and be forced over that mountain. And so as that air is forced upwards, what happens to it? Does it compress or expand? It expands. And so does it warm up or cool down? Cools down. And so we move towards saturation. And so we get clouds. And this is something that you can see if you've ever driven around the Central Valley, if you've explored much of California. You can see that the Central Valley is always pretty sunny. It's relatively dry. We really do rely on that water from the mountains. And that water from the mountains comes because as that air is forced up over those really pretty tall mountains, we cool down, we get clouds, we get much more rainfall, we see different vegetation, we get different climate there. And then if you go to the far other side, who's been to Death Valley or anywhere on the Eastern Sierra? 1, 2, a few. It's really, really dry. It's one of the driest, hottest places in the US, if not the world. It's a very cool place. So how can we have these completely different sort of systems so close to each other? Well, if we think about what's happening as that air moves down the other side of the mountain, does it expand or compress? Compresses. So does it cool down or warm up? Warms up. So do we move towards saturation or away from saturation? Away from saturation. So this is why we have this desert, the other side of this mountain. First of all, we lost a lot of that moisture in sort of precipitation in the mountains, but also as that air comes down the other side, it warms up. That relative humidity drops, and so we get this really dry area on the other side of our Sierra Nevada mountains. We get our Death Valley. And there's a really cool video showing orographic cloud. It's filmed by a slightly strange guy on a microlight, so ignore him to begin with. But as he pans around, you can see really nicely this amazing orographic cloud. He also swears quite a bit. So, can you see that what he's flying over is sort of this ridge, and that air is moving up, And as it moves up that ridge and gets to the top, it's hitting saturation. You can see that cloud forming. Isn't that so cool? I think it's really fun. And so, I know, but I do think it's really fun. So you can really see it. You can see it in action. And so there you go. I'm not just making it up. Okay. So let's think about my second mechanism. So most people have heard a weather forecast at some point in their lives. They'll have heard the word cold front. Yeah? So not on that video. I think it's much more difficult to see. It's not an obvious a process that air diverges. It doesn't flow as nicely down, whereas it's really forced upwards in a nice tight air packet. Okay. So the second one is frontal lifting. So you've probably heard the terms cold front, warm front coming through, and we're going to deal with those much more after the midterm. But frontal lifting is a really important way that we get rainfall, and it's one of the reasons why we care about a cold front or a warm front passing through, because it really will potentially result in rainfall. So when we talk about a front, what we mean is just that two different air masses, so they have different characteristics, they have different temperatures or different amounts of water vapor in them, are coming together. And so in my first example on the left, you can see that there's just sort of warm air hanging out in a particular location, and then we have cold air moving in to try and replace it. And as that cold air moves in, that warm air is forced up and over that cold air, because that warm air is less dense and so more buoyant. So let's just quickly talk about what I mean by density and buoyancy. So buoyancy is defined as the tendency of a less dense material to rise up and float on top of a more dense material. And you know this if you've ever tried to make polystyrene go down in water. It resists, it doesn't want to, it's less dense. That density is its mass over volume. So things like polystyrene and light things have not much mass for volume compared to, say, water or something else, and it's difficult to get them to change position. But when air is heated, it expands, but we don't lose mass. So when air is heated, it gains volume, but its mass stays the same, and so the density of that air decreases. Same thing for water. As you warm up water, it expands slightly, but its mass stays the same, so its density decreases, okay? And then when air cools, it contracts, same sort of thing. And so this is why our hot air balloons work, because as we put heat into the air within that balloon, that air heats up, it expands, it has less dense, it's sort of less dense than the surrounding air, and so it rises, okay? And so here is a nice example of something that is neutrally buoyant. Lots of videos today, but I think they're fun. So here is a guy demonstrating how to be neutrally buoyant. So anyone who's a diver will appreciate this, okay? If he became more buoyant, would he go up or down? Up. If he became less buoyant, he'd sink. So he's perfectly neutrally buoyant right now. And I'm always impressed by this because I tried to go scuba diving once and I did not get it right, and I ended up stuck to the bottom of the boat because I was a little bit too buoyant. So I would love to be able to do something like that. So that's buoyancy. And so the key thing to remember is that that warmer air will always go up. We'll always end up with warmer air over that colder air. So if we think about our fronts again, if we have cold air moving in, it's more dense. So it's going to stay at the surface. It's going to force that warm air up and out of its way. And as that warm air rises, does it compress or expand? Expands. So does it warm up or cool down? Cools down. By the end of today, we'll definitely get this, okay? And then you can see that in my other case on the right-hand side diagram, here I have cold air just hanging out, and warm air tries to move in. But that warm air is still less dense. okay, than that cold air. So what ends up happening is that that warm air instead ends up rising above the cold air. And as that warm air rises, does it compress or expand? Expand. Does it warm? Does it cool? It cools, okay? And so we move towards saturation. Yeah?
You just mentioned that when air moves up, it expands and so it cools down.
Uh-huh.
But in the hot balloon example, how come we say that when air heats it expands and when it cools it contracts?
So in the hot air balloon, we're actively adding energy. So this is, it's cooling because of adiabatic processes. In our hot air balloon example, we're actually physically adding energy, and so it stays less dense, and it can keep rising. If I'm not answering your question, then perhaps you can ask me at the end, and we'll go through it. Okay, great. So let's have a look at a weather map. So here's an example of some of the rain that can form. This is a beautiful example. So if any of you have ever seen a weather forecast, whoever has ever seen a weather forecast? More or less everyone, good, okay. So you can see that ahead of that cold front there, this cold front is marked by these sort of blue triangles, so blue, cold front, it's easy to remember. And you can see that ahead of that, we've got lots of rain. And that's because ahead of that cold air, that warm air is being forced to rise, and that makes it saturated and we get rainfall. You can also see that up at the top we have this red line. That red line is a warm front with those different symbols, and that warm air is moving north. And as that warm air is moving north, you can see that there's also rain associated with that, and that's because of that warm air being forced over cold air. We also get rainfall there. I should have said that green area is marking rainfall. Okay? So third lifting mechanism, we have convergence, okay? And I think in the lecture notes I posted yesterday, there was a slight error. So convergence is winds converge, and so air is forced upwards. So what example did we see last week, last Thursday, where winds start converging, winds start coming together? Where did we mark on our maps where winds were coming together? Low pressure, absolutely. So, for example, for convergence lifting, low pressure systems are an example of why we might get rainfall at these low pressures, because we have winds coming together from all directions and air is forced upwards. As it's forced upwards, it expands, it cools, it hits saturation, and so we're more likely to get clouds and precipitation. So let's look at another example that you haven't seen before. So has anyone ever been to Florida on holiday and experienced thunderstorms there? A couple of people, a few people. It's usually a relief in the afternoon after it's been so hot all day. But can you see that Florida is marked in the little red box there for anyone who's not familiar with America? That seems fair enough. And so you can see that it's this strip of land and it's got ocean either side. So thinking back to what we talked about with specific heat, for example, would the land warm up more quickly during the day or the ocean? The land will warm up more quickly, and so where will air be hotter? Will it be hotter over land or over the ocean? Over the land. So where is air more likely to rise, over the land or over the ocean? Over land. So over land we have this air rising. And what that does is it sucks in cool air from over the oceans. So you can see that my little red arrows there show air rising in the day over Florida, okay, just because it's warmer. But you can see that because that air is rising, it pulls in air from the sides, it pulls in air from over the ocean. And as it pulls in air from over the ocean, that cold air comes in, it's cooler, it's more dense, and so it actually drives further sort of movement upwards. So as those converging sort of sea breezes coming in, it's the same thing that happens here, then they converge over Florida and that forces more air to move upwards. So all of those thunderstorms over Florida are also an example of convergence lifting often. And lastly, we just have localized convection. So those other ones I talked about were really big scale processes. You need a mountain range, you need a large front that often runs for sort of several states or so. Convergence, those low pressure systems are really quite large. Well, we're talking about something the size of Florida. This localized convection can happen at a much smaller scale. So this sort of thing might be what we see in the summer in sort of Texas or in other places where you get little isolated thunderstorms going rather than big sort of tens or hundreds of kilometer scale type things. And it just forms where we get a slightly warmer area of land or whatever, and that air warms up a little bit more, so it becomes less dense, and it just creates its own little convection current. So my challenge for you is we have those 4 lifting mechanisms: orographic lifting, frontal lifting, localized convection, and convergence lifting. Can you work out which of those diagrams correspond to which lifting mechanism? And then I'll ask you an I-clicker question for one of them. Okay? Okay, so let's take a look. Good, definitely. Even has the word front in it, right? So let's think. What is C? Orographic, absolutely. It's always the most obvious one. The second most obvious one is frontal lifting. We have warm air moving into cold air. It says warm front on it. It's a frontal lifting system. The other two are slightly more tricky. What do you think D is showing? Convergence, absolutely, just like over Florida. And so by default, what is A? Localized convergence, okay? Or localized convection, rather, not convergence. Great. So that was the easy part of today. Now I'm going to get you to think, which I know that everyone opposes, definitely. So we are going to talk about stability of air, okay? And this is not difficult once you get the hang of things. So even if you zone out for the rest of today, try and concentrate for the next 10 minutes or so and see if you can get this. So we're going to talk about our lapse rates again, which you remember is how fast things cool down in the atmosphere. So we've talked about our dry adiabatic lapse rate and our saturated adiabatic lapse rate. Does anyone remember what our dry adiabatic lapse rate is? What number? 10, absolutely. So we cool down by 10 degrees Celsius for every kilometer we go up. What about our saturated adiabatic lapse rate? 5, great. And so those adiabatic lapse rates are very predictable processes. They're always the same. It's always 10 or 5, okay? Then we get to talk about environmental lapse rates. This is a bit different. Those adiabatic lapse rate was we were taking air at the surface and forcing it to rise. What we talk about with environmental lapse rates is just if all of the air in the atmosphere was completely stationary, okay, what would be the temperature that we would measure here at the surface and then at 1 kilometer? So we're not changing the position of the air, we're just saying what is the air's temperature here, what is the air like at 1 kilometer, 2 kilometers, 3 kilometers. And that changes. That changes through time because we have day-night, for example. And if you think about what is causing that air temperature difference, it's the fact that we have sort of that radiation, that visible light coming through our atmosphere, heating the ground surface, and then the ground surface is emitting infrared energy, which is absorbed by some of those gases. And more of it is absorbed down here near the surface. It keeps us warmer. We're closer to that heating surface. As we go further up in height, at least in the troposphere, we're just going to deal with the troposphere, then we get cooler, okay? So this environmental lapse rate is just the actual temperature at those different heights, and that can vary. So we have 3 different types of stability. By the end of today, you'll be able to tell me what my air is. And so we have absolutely unstable, we have absolutely stable, and then we have conditionally unstable. So it sort of depends, okay? And it really is a sort of a comparison of what the adiabatic lapse rates are compared to our environmental lapse rates. So the first of my horrible looking diagrams. So I don't want you to focus on this right now. So we're going to deal with absolutely unstable air first, okay? So you can see that on my diagram, I have an environmental lapse rate of 12 degrees Celsius per kilometer. Okay? So let's have a look. So pencils out. So I'm going to have a ground surface here. Here's my ground. Okay. And my air down here at the surface is going to be, I don't know, don't really care, 30 degrees Celsius. Okay? So that's true of just the environment, but it's also going to be true of a little parcel of air. This is my little parcel of air. It's also going to be 30 degrees Celsius. So at the ground, those temperatures are the same. So let's think first about what our environmental lapse rate does. Okay? So our environmental lapse rate, I'm going to shorten that to ELR because it's too much to say. Our environmental lapse rate is 12 degrees Celsius per kilometer. And so what that is telling me is that for every kilometer I go up in the atmosphere, it's going to get 12 degrees Celsius cooler. So if I pick 1 kilometer, so this little dashed line represents 1 kilometer at height, what is going to be the temperature of air at that height? Mental arithmetic. What is going to be the temperature of my air due to the environmental lapse rate? What is what I would just measure if I went up there? 18, absolutely, because it's 30 degrees minus 12. That's how much it's cooling. So it's going to be 18 degrees. So just to reassure me that you know what you're doing, if I went up another kilometer, if I went up to 2 kilometers, what would my temperature be? 6. Great. So that's the environmental lapse rate. That's just what I would measure if I went to those different heights. Okay, we're not moving air around. So now, let's move air around. Let's take my little parcel of air down here, which is 30 degrees Celsius, and let's say that it's dry. Okay? So what's my dry adiabatic lapse rate? 10. Okay. So what is the temperature of the air going to be by the time it reaches 1 kilometer as I force it to rise? What is it going to be? 20. Yeah. So if I force this air upwards, as it gets to here, it's going to be 20 degrees Celsius. Okay? Is 20 degrees Celsius warmer or cooler than the surrounding air at that height? Warmer. Does that mean it's less dense or more dense than the surrounding air? Less dense. Does that mean that if I stop lifting it, will it sink back down? No, what's going to happen to it? It's going to keep going by itself, okay? And so that's even true if you imagine that it went up another kilometer, then up here it would be 10 degrees Celsius. It would be even warmer than the surrounding air, okay? So it's more buoyant. Once you start lifting it, it's going to keep going by itself. And that's what we call absolutely unstable air, okay? So let's double check ourselves. Let's double check that that's true in all cases. So let's imagine my other sort of scenario. Let's imagine that even down here at the surface, my air is completely saturated. So now let's think about what would happen with the saturated adiabatic lapse rate. And how much is that? 5. That's right. So 5 degrees Celsius per kilometer. So what would the temperature of that air be by the time it reaches 1 kilometer? 25? Is that cooler or warmer than the surrounding air? Warmer. So in this case, it doesn't matter whether it's cooling at the dry adiabatic lapse rate or the saturated lapse rate. Once I lift it a little bit, it's just going to keep going. Does that make sense? Maybe? Hopefully? So, let's think about something different. Okay, so let's think about a case. So here's my ground again. I'm going to do exactly the same exercise. So temperature at the ground is 30 degrees Celsius. I have a little parcel of air at 30 degrees Celsius. Parcel of air at 30 degrees Celsius. So now my environmental lapse rate is going to be a bit different. It's going to be much less dramatic than it was before. It's now just going to be 3 degrees Celsius per kilometer. Okay? So 3 degrees Celsius per kilometer. So if I go up 1 kilometer in the atmosphere, what's the temperature going to be of the surrounding air? 27. What is it going to be by the time I get to 2 kilometers? 24. Okay. So now let's think about completely dry air. So this is the dry adiabatic lapse rate of 10 degrees Celsius per kilometer. What's the temperature of this air going to be by the time it hits 1 kilometer? 20. Is that air cooler or warmer than the surrounding air? Cooler. So is it going to be less dense or more dense than the surrounding air? So is it going, if I stop lifting it, is it going to keep going or is it going to sink? It's going to sink, okay? It's stable. It wants to stay as it is. It doesn't want to rise. It wants to stay at the surface. It's stable. So now let's double check ourselves. Now with the saturated adiabatic lapse rate, which is 5 degrees Celsius per kilometer, what will the temperature be as I reach 1 kilometer? 25. It's always the same. Okay? So is that warmer or cooler than the surrounding air? Cooler. Is it going to continue to rise or is it going to sink? It's going to sink. So it's absolutely stable. Doesn't matter if it's dry or if it's saturated. If we remove that lifting mechanism, it's going to sink back down. It's stable. It doesn't want to go anywhere. Okay? So, third example. Ground surface. We're still going to pick 30 degrees Celsius, but it could be anything. I could pick 20, I could pick 10, it would still work. Okay? So now, my adiabatic lapse rate, my environmental lapse rate is going to be 7 degrees Celsius per kilometer. Okay? So here's my parcel of air, 30 degrees, 30 degrees. So what is the temperature going to be at 1 kilometer for my environmental lapse rate? 23. What would it be at 2 kilometers? No one can do the maths anymore. 16, yes, I think. So what about if my air was dry? So my dry adiabatic lapse rate. What would happen if I lift that air? What temperature would it be at 1 kilometer? 20. Is it warmer or cooler than the surrounding air? Cooler. Is it going to continue to rise or is it going to sink if I stop lifting it? It sinks. Okay. So what about the saturated adiabatic lapse rate? This is going to be 5 degrees Celsius per kilometer. What's the temperature going to be here? 25. Is that warmer or cooler than the surrounding air? Warmer. What's going to happen? Is it going to sink or continue to rise? It's going to continue to rise. So let's think of a different situation. So let's say that my air started off dry, but let's say it hit saturation at this particular altitude. So from this point on, it's actually going to follow the saturated adiabatic lapse rate instead. Okay? So what's the temperature of this parcel of air going to be by the time it hits up here? It's going to be 15 degrees. Okay? It's actually getting close again. If we went up another kilometer, don't have room. So what would the temperature be of the surrounding air? 9. If this was still saturated, what would the temperature be? 10. So now we have something a little bit more complicated. So first of all, the simplest example was that depending on whether it was dry or saturated at the surface, means we could either get stable air that would sink back down or air that would continue to rise by itself. But we don't often get air that's completely saturated at the surface. Instead, that tends to happen after we've lifted that air by a certain amount. So what we can say is, well, let's think of a more realistic scenario. It might be dry to begin with, and so if I lifted my air 1 kilometer, okay, and if I stopped lifting it at that point, it would be stable, it would sink back down. If I kept lifting it another kilometer, It's getting closer, but it's still cooler than the surrounding air, and so if I stopped lifting it up, it would sink back down. But if I can lift that air another kilometer, then what happens is that now it's warmer than the surrounding air, and it will actually keep going by itself. Okay? So it's conditionally unstable. Depends whether it's dry or saturated, and it depends how high you can lift it. Okay? So does that make sense to everybody? You think you could do this? In, for example, I don't know, a quiz? Maybe? We'll see. Okay. So this is sort of basically, I just drew out what we did just there. Okay? I think that's by far the easiest way of doing things, is just to draw it out for yourself. Okay? And so here's my absolutely unstable air. You can see that my environmental lapse rate is higher. It's a larger number than my dry or saturated adiabatic lapse rates. And so whatever happens, then that air is going to continue to move upwards once I lift it a little way. My second example, my environmental lapse rate was 3 degrees Celsius per kilometer. That's much less than both the dry and the saturated adiabatic lapse rates. And so whatever happens as I go up in the atmosphere, whenever I stop lifting that air, it's going to sink back down. It's going to be cooler. It's going to be absolutely stable. It doesn't want to go anywhere. Okay? But we have our conditionally unstable. So this is when we have an adiabatic lapse rate that's between 5 degrees Celsius and 10 degrees Celsius per kilometer. Okay? So it's a pretty special case. And it depends on a couple of things. It depends on, first of all, whether your air is dry or not to begin with. Okay? If it's completely dry, then it's going to be stable. But if you reach a dew point, if you start condensation happening and you can continue to lift it, then at a certain point, so for example, when we saw it about 3 kilometers, at a certain point, that air will become unstable. It will start going by itself. And we call that altitude, that 3 kilometers, that height that we had to force that air to get to before it would start going by itself, we call that the level of free convection. Make sense? At that point onwards, it will keep going by itself. It will convect by itself. Does that make sense? Hopefully. Not too bad? Okay. So, prove to me it's not that bad. So my environmental lapse rate is 6 degrees Celsius per kilometer. Would that parcel of air be absolutely stable, absolutely unstable, or conditionally unstable? Strange. Okay. Not good enough. I'm going to make you draw it. Okay, so just like I did before, think about the environmental lapse rate. Think about what air would be at the dry adiabatic lapse rate, how much it would cool down, what it would be at 1 kilometer. And what about if it was saturated? Right, let's take a look and see if we did better that time round. Yes, we did. Either that or everyone just clicked on the most popular one. But either way, you're right. Okay, because if that's 6 degrees Celsius per kilometer, if we start at 30 degrees at the ground surface, what will it be at 1 kilometer, just due to the environmental lapse rate? 24. If we start with that air and it's dry, what will it be at 1 kilometer as we force it to rise? 20. Is that warmer or cooler than the surrounding air, which is 24? Cooler, so it's more dense, it would sink. If it started off saturated, what would it be by the time we forced it to rise by 1 kilometer? 25. Is that warmer or cooler than the surrounding air at 24? Warmer. So that air would rise. Okay, it's conditionally unstable. Okay, so have a go at practicing that. Set yourself a challenge with different environmental lapse rates. So we have a special case. So with our environmental lapse rate, we've always been assuming that it's constant as we go up in the atmosphere, and that it always gets colder as it goes up in the atmosphere. And that's not necessarily true. Sometimes we can end up with warmer air sat on top of colder air at the surface, okay? And so do you think, oh, I put it in the title, so I'm not going to ask, but that means it's extremely stable because it's already colder than what's above. It's going to be really, really difficult to force that air to go anywhere, okay? And you can see really fun examples of this at different times of year in different places. So here's a really fun time lapse again, showing what happens when we get one of these inversions. And we have this air moving and it can't go up. And so we get beautifully clear air up above and very fast hikers. And sort of this sort of cooler air underneath. And so I think this is really pretty. Can anyone think of somewhere where we might see something similar? If you were quick enough, you probably saw the next slide. Where do we sometimes see clear air above not so clear air? Have you ever looked northwards towards LA? Do you ever see something that looks like that? Yeah? So here we have this sort of nasty, particularly nasty smog layer. We're going to talk more about what causes that at the end of the quarter. And yes, a lot of that pollution is produced here at ground level. But if we have air moving, then that pollution can disperse. It can go up in the atmosphere. It can go other places. But what happens in Los Angeles is we're under this nice high pressure. And remember, in a high pressure, we have air moving downwards, okay? And as it moves downwards, does it compress or expand? Compresses, so does it warm up or cool down? Warm up. So we sometimes get these inversions. We quite often, in fact, get them around Los Angeles and Southern California, where we have this warmer air above cooler air, and so that pollution is trapped. And you can see that inversion layer. So next time you're driving through and up to LA, you can point out the inversion layer to your family and they'll be impressed. So, yes. So, let's move on to clouds. Not that we have very many examples out there today, but clouds are everywhere on the Earth. So, we have traditionally 4 basic types. We have cirrus, which are really thin, wispy, sort of icy clouds. We have stratus, which are layered. And then we have cumulus, which are when you have sort of vertical development, so they're sort of vertically extensive. And then nimbus, which are rain-producing clouds. So if anyone talks about nimbus clouds or cumulonimbus, it means it's going to rain on you. And then people decided that was too simplistic, and they split it into 10 types of clouds. And then we have high clouds, middle clouds, low clouds. I don't want you to memorize the 10 different clouds. I don't want you to even write them down on your card. Okay? If you want to know what a cloud is, I'm sure you can look it up. You're all very good with Google. But what I would like you to be aware of is that there are different types of clouds based on height. Because those different clouds at different heights act on the climate system in very different ways. Okay? So our high clouds are above 6 kilometers. So they're still in the troposphere, okay, they're still in that lowest layer of the atmosphere, but they're much higher up. They tend to be icy. We have these middle clouds from 2 to 6 kilometers, and then we have low clouds which are below 2 kilometers. And then vertical development, if you see some of those big thunderstorm clouds go up in the summer, if you look towards the mountains, they go and they span a huge amount of that atmosphere. They go right through those different levels. So here's a little diagram showing some of those, what they look like if you're particularly interested. I am not going to give you a photo of a cloud and ask you to identify it, but they are beautiful things, and if you would like to know more about them, there's lots in the book. In general, you can see that these are our high clouds. They're what we're quite familiar with here. They're those wispy things up in the sky. Do they affect our temperature down here very much? Do you tend to see a shadow as they come over? Not really, okay? So do you think they're affecting our albedo very much? Not really, okay? So we're going to come back to that idea. So here are our middle clouds. So stratocumulus, so altocumulus or altostratus. These are our low clouds, stratocumulus, stratus. These are our really fun ones. We have clouds with vertical extension in the atmosphere. We have cumulus and nimbostratus, and by far my favorite type of cloud, because everyone should have a favorite type of cloud, is the cumulonimbus. And these are our big thunderstorm clouds. They're associated with our big dramatic weather. And you've seen these, right, go up over the mountains in the summer, inland from us. And you can see that they often have this really flat top. Does anyone know why they have this flat top? What you're seeing there, what you're seeing along that flat top, you're seeing the barrier or the line between the troposphere and the stratosphere. So they reach the stratosphere, it starts getting warmer again. It acts just like our inversion. And at that point, they can't go up anymore. They form this big flat line, these sort of anvil-shaped clouds. And that's marking the boundary between the troposphere and the stratosphere. So these are really vertically extensive. Okay? So how do clouds affect global temperatures? This is actually a really important question for understanding how our future climate change might play out. So we have two different effects. If you remember, we talked about this last week. We said that clouds during the day, especially if they're thick clouds, can act to reflect back incoming radiation. They change our albedo, so they cool us down. Okay? But clouds can also capture or absorb some of that outgoing infrared radiation. Okay? They're very good at acting to basically increase that sort of greenhouse effect and keep us warmer. But how much radiation a cloud absorbs depends on its height as well. And we saw that those different clouds would also have different effects on albedo. And so the bottom line is that high clouds, those really nice wispy ones that we see outside, they result in warming. They're not really blocking much of the incoming light, but they do act to trap energy that would go out. But low clouds, the ones that would sort of cast a shadow as they come across, they tend to result in cooling of the planet. The albedo effect sort of wins out in that case. Okay? So we have these two different things going on. So, because I know how much you enjoyed feedback loops, let's think about feedback loops. So do you remember this notation? We used this when we talked about the snowball Earth and what happens to albedo. So if I increase temperature, what am I going to do to the amount of water vapor in the atmosphere? Am I going to increase it or decrease it? Increase. We'll have more evaporation. So what type of arrow would I need to use? Would I need to use a normal arrow or an arrow with a circle at the end? The normal arrow. If I increase the amount of water vapor in the atmosphere, what is going to happen to the amount of outgoing energy absorbed by the atmosphere? Is it going to increase or decrease? Shall I ask again? So if I increase the amount of water vapor in the atmosphere, what is that going to do to the amount of the outgoing radiation that's absorbed? Is it going to increase or decrease? Increase. So what arrow would I use? The normal arrow again. If I'm increasing the amount of outgoing radiation absorbed, am I going to increase or decrease my temperature? Increase. Okay. So am I going to have a normal or a weird arrow? Normal. Okay. So yeah, we have this positive feedback loop going on. If we increase temperature, we increase the amount of water vapor in the atmosphere, we increase our greenhouse effect, so we further increase temperature. It's a little positive feedback loop. It's a destabilizing loop. But that's all very well, but we haven't taken into account clouds and albedo, right? So there's the loop we just did. Okay? So we go from increasing temperature to increasing water vapor, which increases the amount of outgoing radiation absorbed, and that increases temperature. So what I want you to do, your challenge for the next 5 minutes, is to complete my feedback loop for the other side. Okay? So the TAs will wander around and help you out. Okay? See if you can complete my loop. And then if you do, think about the question I ask at the bottom. Okay, let's take a look and see how we're doing. Okay, quieten down for 2 more minutes, please. I still have a few minutes left. So, you all put decrease. Why decrease? Because of albedo. But what about that side? If I follow this loop around, what will increasing amounts of outgoing terrestrial radiation absorbed due to temperature? Increase. So this is our problem. If we follow that loop around that way, we have an increase. If we follow our loop around this way, we have a decrease. So in reality, this isn't a trick question. The right answer is we're not sure. And this is something that... Shush. One more minute, please, guys. One more minute. So, and this is something that we are really struggling with in our climate models. It's very difficult to model clouds. Clouds don't come in nice kilometer by kilometer chunks, and we need to make sure we get them the right height and everything else. So clouds introduces a lot of climate uncertainty. I'll see you on Tuesday.